Here's the solution to the problem involving the tree log being dragged across level ground. You can see a tree log is dragged across level ground to the right at a constant 3 meters per second by a cable attached to a tractor. Cable tension 600 newtons and the log weight is 1,000 newtons. Let's take a look at our parameters. Is this at rest? It is not. Okay. Is it a constant velocity? Yes. We see it's at a constant 3 meters per second. So we'll say yes. Okay, now the other condition, are the forces balanced? Remember, if we're either at rest or we end up having constant velocity, then our forces are balanced. Another way of saying that are the net forces, sorry about that, net force, we also can write that as the sum of forces is equal to 0. Next, what I'll want to do is make an interaction diagram and a force diagram for the log. I'll start putting this interaction diagram together. It'll just pop on your screen in a moment here. Here, so I've made a little drawing of the situation. We have our log being pulled to the right, 3 meters per second by a trailer, and a cable hooked up to that. I've drawn in the ground and the earth. Let's go ahead with our interaction diagram. First, let's talk about the non-contact forces. The only one we're talking about right now is gravity. Gravity, I'll know that the log is being pulled down by the earth, so I put a little G here. There's me on the tractor. Okay, the ground is being pulled down. And we could say the cable as well. Or a lot of times we'll just ignore that. So we've taken care of the non-contact forces. Contact forces. For some, let's talk about normal or pushing between those. Hey, certainly the log on the ground, that's one force of one place we'll see normal force. Our tractor pushing on the ground, ground pushing on it. And I don't really see any other normal forces there. Okay, so normal. Let's go our next one. Take a look at tension. The place I see the tension between the log and that cable, T for tension there, and between the tractor and that cable, tension there also. All right, last one is friction. Remember, friction is the force that wants to either resist motion or resist impending motion. We see that friction between the tractor and the ground, okay, and also between the log and the ground. So you draw that in right over here. Okay, so I've got that taken care of. Prepare for my force diagram. I'm going to enclose the object as closely as possible. And then anytime it cuts through one of those interactions or forces, I make a note of it. So I have gravity here. Remember, my log becomes a single dot. I've got a force of gravity on the log from the earth. That's right. It's from the earth. Take care of that one there. Come around over here. Here, there's a normal force that's going to move at a constant velocity. Forces are balanced. So I have a normal force on the log from the ground. These will be of equal length. Coming around over here. Okay, I see I have a, let's see, tension force. That's going to be pulling to the right. Force of tension on the log from the cable. Hey, this isn't balanced right now, so I know there's going to need to be another force to the left. Hey, it must be this frictional force. Can I draw it in there? Yeah, it looks like I drew in friction here. Friction, we know that's going to oppose that motion. To balance, we know it has to have an equal magnitude. Force of friction on the log from the ground. Okay. Let's go put some numbers in here. Earlier we saw that. Let's see if it's listed up here. Cable tension is 600 newtons, so I'll put 600 newtons here. So I know that my tension force must also be 600 newtons. Weighted log is 1,000 newtons. So that normal force must also be 1,000 newtons. Let's scroll down the screen. We'll see about these graphs that we need to take care of here. So let's go take a look at those. Let's go ahead and finish up these graphs. Okay, we have a position versus time graph and a velocity versus time graph. Okay, let's go ahead with this position versus time graph. Okay, I'm going to go up till 10 seconds here. I know it was moving at 3 meters per second. Let me fill in these units so I know time is going to be in seconds. And we were traveling at 3 meters per second. So I've labeled my x-axis for time with the unit seconds, and we're going up to 10 seconds. It was traveling at 3 meters per second to the right, so after 10 seconds, that's going to be 3 meters per second times 10 seconds. It'll travel 30 meters. I'm going to make sure I put appropriate labeling for the vertical axis. So I've labeled this axis in units of 5 meters. Oh, here's my error. It should of course be meters, not meters per second. Up to 30, 35, 40, so on. We're only going to have to go to 30. So it's traveling at constant velocity, so that's a straight line on a position versus time graph. Let's see if I can put that in there. What just happened? Yeah, there, okay. Hey, over here on the velocity versus time graph, velocity is going to be in meters per second. Again, time is going to be in seconds. Just labeling these axes in 1 second increments per division along here, and also 1 meter per second divisions here. We've got 0 in the middle here. I know it's going, as stated before, traveling at 3 meters per second. You can go ahead and put that along here. Remember, its velocity is constant. If we have some quantity that's constant, that stays horizontal in its graph. This one, velocity, stayed at 3 meters per second throughout those 10 seconds. Last question here. If the tractor drags the log for 1 minute, how far will the tractor have dragged the log? Use the 5-step process. Say below rather than the backside. The backside is the other problem. Let's get this started. So the picture is drawn above. Find the distance. That's what we're trying to find. Given that our velocity is 3 meters per second and our time is 60 seconds. Yeah, our relationship is the rate time distance problem you learned back in grammar school. So rate times time is equal to distance. And in this case, our rate is known as our velocity times time is equal to distance. All right, let's go ahead and solve this thing. Okay, my velocity is 3 meters per second. My time, you can see that I converted from 60 minutes to seconds. 60 seconds. I went 180 meters, about twice as long as the baseball field. Could a tractor drag a log that far? Yeah, passes a smell test. And we'll zoom out on this. And here's the completed worksheet.